This is a joint work with my PhD supervisor, Professor Jie Lu. This talk will include 5 parts. The first part introduces a lot of examples to show why distributed optimization is important. The second part describes the distributed optimization problem that we focused on. After that, I will talk about the development procedure of the proposed algorithm. We also study the theoretical convergence of the proposed algorithm, where the convergence result is shown in the first part. And finally, we test the practical performance for a specialization of the proposed algorithm. Distributed optimization is based on networks. As a development of communication technique, more and more devices in our life are connected by networks, such as computers, cell phones, smart watches, and even cars. Such a network is called the Internet of Things. And it is estimated that at 2025, there will be approximately 80 billion network devices, 180 trillion GB of data, and 4 to 11 trillion of USD dollars involved with Internet of Things. In many engineering scenarios, nodes in a network need to cooperate to complete certain tasks. This is an example in data networks. Suppose there are 2 source nodes and 1 destination nodes. And the 2 source nodes want to transmit data to the destination nodes through the network, which includes 3 links. In this figure, x1 and x2 are the amount of data sent by node 1 and node 2. And the u1 and u2 are the corresponding utility function. These 3 links has capacity C1, C2, and C3. And for node 1, the path to destination node includes link 1 and link 3. And for node 2, the path to the destination node include the link 2 and the link 3. An interesting problem is to find the value of x1 and x2 so that the total utility can be maximized. Such a problem can be formulated into this optimization problem, where each row of the constraint represents the capacity restriction of each link. Another example is data estimation in wireless sensor networks. Suppose there are 7 sensors in the network, and the task is to estimate the position x of the target. In this network, each sensor has an observation wi on x. If we directly let a wi to be the estimation of x, then the accuracy may not be good enough. However, if we choose the average of all the wi's as the estimation of x, then the accuracy will be improved. The average of all the wi's can be solved from this optimization problem. This problem is also one of the most classical problems in distributed optimization. Distributed optimization also has many applications in power systems, such as economic dispatch. Suppose there are 7 power generators in the power systems, and the total power demand at a time instance is D. For each power generator, Xi is the amount of power generated by this power generator, and the Cixi is the corresponding cost. Each power generator can only generate power in this interval. Then it is natural to ask, what is the optimal policy for these power generators to generate to meet the power demand with the minimal total generating cost? This problem can be described by this optimization problem. Distributed optimization also has many applications in other research areas, such as multi-robot systems and water distribution networks. Now we introduce the problem that we focused on, which is an important class of distributed optimization problems. The network model is described by a graph G, where V is the vertex site and E is the edge site. In this network, we require each node to have a local division variable xi and a local objective function fi, which measures the cost for making the division xi for node I. Then, an interesting problem is to find a common division variable which minimizes the sum of all the local objective functions. This problem can be described by this optimization model. Okay. This problem has many applications in cooperative control and machine learning. The state estimation problem that we introduced before is also an example in which the local objective function fi is the norm square of xi minus wi. To solve this problem, we need to face two challenges. First, in this network, only neighboring nodes can communicate with each other. Each node makes its own division based on information from its neighbors, and all nodes in the network cooperate to find the optimal solution of the problem. The second challenge is due to the privacy issue. In the network, each node cannot share its local objective function fi to the other nodes. My research considers how the algorithm should look like, so that the optimal solution can be found quickly, both in theory and in practice. There have been a large number of algorithms for solving this problem. Many of the state of the art are developed in the last decade. However, these algorithms are developed based on different ideas and have different algorithm forms, so that it is difficult to understand them and to understand and compare them from a unifying perspective. In addition, many of these algorithms require restrictive problem assumptions and have incomplete or unsatisfactory theoretical convergence results. Motivated by this, we propose a class of distributed algorithms that generalizes many existing algorithms. We also theoretically analyze the convergence of the algorithm and derive superior theoretical convergence result, which improves that of many existing algorithms. In addition, the proposed algorithm can also be specialized to novel algorithms with powerful practical performance, which is demonstrated by simulation examples. Now we'll go to the algorithm development part, which includes a lot of mathematics. So first, we split each local objective function fi into a smooth function, lowercase fi, and a possibly a differentiable function fi, lowercase fi, and a possibly non-differentiable function hi. Of course, we can directly like hi be identical to the function capital fi, so that the differentiable function lowercase fi is a zero function. If this problem includes a local constraint like this, then we can write hi xi to be the indicator function of this constraint, where the indicator function is described here. We assume the underlying graph to be undirected and connected. Okay. Okay, the development procedure of the algorithm includes 4 steps. We first make a problem transformation, and then use the method of multipliers to solve the resulting problem. However, the method of multipliers cannot be implemented in a distributed way over the networks. To solve this issue, we approximate the method of multipliers using a surrogate function, and then design the surrogate function properly for distributed implementation. In the problem transformation, we first rewrite these local division variables and these local functions as a compact form, so that the objective function can be rewritten as fx plus hx. We also look for symmetric and positive semi-definite matrix H to transform the consensus constraint that all the x's are required to be identical into a linear equation hx equal to 0. Note that we require the matrix H to be symmetric and positive semi-definite, so that the square root of H exists. And the linear equation hx equal to 0 is equivalent to the linear equation square root hx equal to 0. We also require the matrix H to be sparse with respect to the underlying graph T, which means that if I and T, load I and load T, if I does not equal to T and the ij are not neighbors, then the ij block of the matrix H is 0. An example satisfying these requirements is given by this one. Here, Ni is the neighbor site of node I, and D is the dimension of each variable xi. When D equals to 1, then this matrix is actually the graph Laplacian matrix of the underlying graph. The matrix H in this example satisfies symmetricity and the positive semi-definite, and is sparse with respect to the underlying graph T. In addition, hx is equal to 0 if and only if all the local variables xi are identical. Now we have transformed the original problem into this compact form. Now we use the method of multipliers to solve the problem. The method of multipliers include 2 updates at each iteration, include a primal update for the primal variable x and the dual update for the dual variable v. The method of multipliers perform well for solving this problem. However, it cannot be implemented in the networks. To see this, we suppose that the function f and the function h supposed to be a variable function, and that each node I maintain the variable xik and the vik, which are the s blocks of the variable xk and the vk in the method of multipliers. With this setting, the method of multipliers will become to this one, where xk plus 1 is a solution, closed form solution of this. And the update of x, here, this matrix is the pseudo inverse of the square root of h. Now the update of xik and the vik will have this form. So that although previously we require the matrix H to have a sparse structure, which means that if I does not equal to T and ij are not neighbors, then the ij block of H is 0. However, the square root of H and the pseudo inverse of the square root of H does not have such a sparse structure. So that we can see from this updates that the calculation of xik plus 1 and the calculation of vik plus 1 will require vgk and xgk, even if I does not equal to G and ij are not neighbors, because this part is not variable. Okay, this is the former method of multipliers. In this slide, we will approximate the method of multipliers using surrogate function so that it can be implemented in a distributed way. We first substitute fx in the update of xk by a surrogate function uk, and then make a change of variable for the variable new variable vk and obtain a new variable to the vk. Then the algorithm form will become this one. This algorithm can be implemented over the network for proper defined surrogate function uk. However, it is not general enough. In order to include more existing algorithms as the example of the proposed algorithm, we substitute this matrix H in the due update by matrix tilde H, so that the algorithm will become to this one. We require hx equal to 0 to be equivalent to tilde hx equal to 0, and the matrix tilde H to be sparse with respect to the underlying graph T. An option is to write tilde H equal to H. Then know that the update of tilde vk can be rewritten as this one. For each I, it will have this update. Since we require that the matrix tilde H to have a sparse structure, so that if I does not equal to G and the ij are not neighbors, then the ij block of tilde H will be 0, so that this one is equivalent to this one. But from this update that only xgk plus 1 from the neighbor of node I are required, so that this update can be implemented over the networks. We still need to design proper surrogate functions so that this primal update can also be implemented over the networks. We choose the surrogate function uk to be in this form, where d phi k is the fragment versions of a function phi k. We have designed a lot of options in our paper. However, for simplicity, here we only introduce one option. We can let phi k to be the summation of a set of functions psi ik minus this quadratic term. This quadratic term is actually for eliminating this quadratic term in the method of multipliers. With this design, the update of xk will be equivalent to this one. Note that in the first 3 items, only information of node I itself is needed. And in the 4th item, only xgk from the neighbor of node I is needed, so that this update can actually be implemented over the networks. We provide 2 options of psi ik. For example, psi ik can be a quadratic term, a norm square, and the psi ik can be in this form. For the first option, the resulting algorithm will be a first-order algorithm, and for the second option, the resulting algorithm will be a second-order algorithm. We found that the proposed algorithm generalizes over 10 state-of-the-art algorithms, and many of them are quite famous and classical in distributed optimization. We also extensively studied the theoretical convergence of the proposed algorithm. To introduce our result, we first give the definitions of convex and smooth. It is shown in these 2 definitions. And here, partial fx and partial fy are the subgradients of the function f at x and y respectively. These 2 assumptions, we require each fi to be convex and smooth, and the function hi to be convex. This assumption is a standard assumption in convex optimization, and is very less restrictive. Under this assumption, we use this design of the surrogate function UK, where in the definition, here the matrix A is required to be positive semi-definite and block diagonal. Although this form is quite simple, it still generalizes many existing algorithms. Under this assumption and the setting of the surrogate function, we derive convergence results for the running average of the primal variable xik, which is the average of all the xit from t equals to 1 and t equal to k. We prove that both the objective error and the consensus error of the proposed algorithm converge with a convergence rate of big O of 1 over k. Here, f star is the optimal objective value of the optimization problem. We also derive convergence result under another assumption. Here we first give some preliminary knowledge. Here are the definitions of strongly convex, locally strongly convex, and the locally restricted strongly convex with respect to a point Q(x). For these definitions, locally strongly convex is stronger than locally strongly convex, and locally strongly convex is stronger than locally restricted strongly convex. We require the summation of Fix to be locally restricted strongly convex with respect to the common optimal solution X star. Note that for our problem, the form of the optimal solution should be X1 star, X2 star to Xn star. However, the constraint requires that all the Xs to be identical, so that all the Xs star will be equivalent and will be identical to a common X star. This assumption is less restrictive than the assumption that the summation of all the Fix to be locally strongly convex, and is less restrictive than the assumption that each Fix to be locally strongly convex and each Fix to be strongly convex. Here we give an example. Suppose F1x equal to 1 over x squared, and the F2x to Fnx to be a zero function. Then the summation, then F1x is locally strongly convex, so that the summation of Fix is locally strongly convex. However, we can see that F2x to Fnx is not even locally strongly convex. That is not satisfying these two constraints, these two assumptions. Under locally restricted strongly convex assumption, we are able to use the general form of surrogate function, which is introduced before. Here we require each phi k to be strongly convex, smooth, and enable distributed implementation. Under this, under this setting, we derive convergence result for two cases. If the possibly non-differentiable function Hix is not a zero function, then we prove convergence result for the running average bar xik. We prove that both the objective error and the consensus error converge to zero with a convergence rate of big O of 1 over k. This is the same convergence result as before. However, in this setting, we are able to use more general form of surrogate function. If in addition, each Hix is a zero function, then the iterate xk will converge linearly to the optimal solution. Our convergence result provide new convergence result for many existing algorithms. In the case where each local objective function is not locally restrictive strongly convex with respect to the optimal solution, our result relax problem assumptions of some algorithms from smooth or constrained smooth to non-smooth, and also improve convergence of objective error and consensus error for some algorithms, including, you can see for objective error from asymptotic to big O of 1 over k, and for consensus error from big O of 1 over square root k to big O of 1 over k. If the local objective functions are locally restricted strongly convex to the optimal solution, and if HIX is a zero function, then our result relax the global strong convexity of each Fi from many, which is assumed in many existing algorithms, to local restricted strongly convex. And we also provide new linear convergence result for many existing algorithms, where the linear convergence is absent in the literature. To test the practical performance of the proposed algorithm, we consider a constrained L1 norm regularized problem, which is shown here. For this example, each Fix is a projective term, and each HIX is a L1 norm term plus a indicator function. This indicator function describes the local constraints. This is a result for objective error. We compare 4 existing algorithms, including PGXtra, DFBBS, DPT, and the distributed ADMM, with the specialization of our algorithm, which is referred to as DAMM. Yeah. In these 2 figures, we plot the convergence of running average bar XIK and the convergence of the master iterate XIK. The x-axis is the number of iterations, and the y-axis represents the accuracy. From these 2 figures, we can see that both the running average and the master iterate of the specialization of our algorithms converge faster than the other algorithms. And the master iterate converge much faster than the running average. However, the curves of running average is much more smooth than that of the master iterate. These 2 figures plot the convergence of consensus error. You can see that in these 2 figures, the specialization of our algorithms also converge faster than the other methods. To conclude, we have stated that distributed optimization is important in many research areas, including data networks and power systems. We provide a unifying algorithm framework for many state-of-the-art distributed algorithms. Our convergence result also relaxes problem assumptions of many algorithms and provide better convergence result. We can also specialize novel algorithms with competitive practical performance from our proposed algorithm. That is all, and thank you.